Transforming quadratic functions. Our objective is to graph and transform quadratic functions. Why learn this? You can compare how long it takes raindrops to reach the ground from different heights. Earlier in the course, we learned about the parent function for a linear function. Now, we're going to learn about the parent function for a quadratic function. So we have f of x equals x squared. You can think of it as y equals x squared if that helps. The axis of symmetry is going to be x equals 0. So your axis of symmetry is your y-axis for the parent function. Your vertex is going to be at 0, 0. And the function is only going to have that one 0, and it's at 0. Okay, so your parent function stretches up the same way, so it's like it comes up 1 and over 1 to the right, up 1 over 1 to the left, and then your next point would be up 1, 2, 3, 4, and then over 2 to the right and 2 to the left. So your parent function is always going to follow this pattern. It starts at 0, 0, it increases at the same rate on both sides, and the axis of symmetry is at 0. So now let's look at comparing coefficients in the following functions. So we're looking at our a value. So our b and our c are staying the same. Nothing is happening to that. We're only changing the a. Okay, so that would be in ax squared plus bx plus c. The a is this value in front of the x squared. It's the coefficient. The things that stay the same are going to be the axis of symmetry and the vertex. So the a value does not change this. What it does change is the width of the parabola. So it makes it narrower or wider. To be more specific, the graph of f of x equals ax squared is narrower than the graph of f of x equals x squared if your absolute value of a is bigger than 1. It's going to be wider if it's less than 1. So your parent function is this red one right here. It's the f of x equals x squared. Then if we look at h of x, notice how this value of a is less than 1, so it's wider. G of x has an a value of -2, so its absolute value is greater than 1, so therefore it's going to be narrower. The negative, all it does is change the direction of the parabola, whether it faces or opens downward or opens up. So let's practice. Comparing widths of parabolas, we're going to order the functions from narrowest to widest. So step 1 might be to find our absolute value of our a values. So we have f of x, our a value is going to be 2. Our g of x, our a value is going to be 1/3. And h of x, our absolute value would be 4. So now we can order the functions from narrowest to widest. So our narrowest graph is going to be the one with the bigger number here. So we have h of x equals 4x squared as our narrowest. Our next narrowest is going to be the f of x. So we have f of x equals -2x squared. And then we have g of x equals 1/3 x squared. So now, take a moment and pause the video and try these next two on your own. When you return to the video, the answers will be revealed below. And there you have it. Keep in mind, if two functions have the same absolute value for a, they're going to have the same width. Alright, so now let's try comparing the coefficients with these following functions. Notice how the a and the b values stay the same this time. However, the c values are different. That means your axis of symmetry is going to stay the same, and the width of a parabola is going to stay the same. Because remember, the a value changed the width. So if the a values are all the same, the widths are going to be the same. The vertex of a parabola, however, changes because your c values change. And since your c values are your y-intercept and your axis of symmetry is still going to be x equals 0, that means the graph is simply going to move up or down. If c is larger than 0, the graph is translated up, whatever that many units was. If c is less than 0, the graph is going to be translated down, whatever the c value was. So let's practice. So we're going to compare the graph of each function with the graph of f of x equals x squared. So we're going to compare each of these with the parent function. So in this case, g of x is wider because of this a value. It opens downward because of this negative. So it's wider because it's less than 1. It's opening down because it's a negative. And now we have our c value. In this case, it's a positive 2. So it's going to translate up 2 units. And when I refer to it, I mean the vertex. To be a little more specific. Okay, take a moment, pause the video, and try this next one on your own. When you return to the video, the answer will be revealed below. And there you have it. The formula used to approximate the height in feet above the ground of a falling object in t seconds after it is dropped from a height of c feet. So this is a good formula to kind of have in your notebook there. So we have h of t equals negative 16t squared plus c. So now let's put this to good use in a physics application. Two identical water balloons are dropped from different heights as shown in our diagram. Step 1. Write the height functions. The y-intercept c represents the original height. You can think of that as your y-intercept, since its initial height, that's at time 0, and it starts at 64 feet up and at 144 feet up. So when we write our functions, we're going to have it starting at 64 feet and 144 feet. So now you can use a graphing calculator. Since time and height cannot be negative, set the window for non-negative values. When does each water balloon reach the ground? To do that, or answer that question, you want to look at your x-intercepts. So where does the graph hit that x-axis? That's also when it hits the ground. So the balloon that was dropped at 64 feet will reach the ground in 2 seconds, and the balloon dropped from 144 feet is going to reach the ground in 3 seconds. So that's how you can use a graphing calculator to help you read the changes that are happening or the transformations that are happening with your graphs. This also ends our video on transforming quadratic functions.